In this session, we'll be talking about the different kinds of distribution, right? So, we will initially get started with understanding what is the difference between parametric versus non-parametric distribution. How do I really differentiate between these two? Then we'll start talking different kinds of distribution. We'll see what do we mean by uniform distribution. There are different more commonly used kind of distribution. So we'll see what is the uniform distribution. We'll see what is a Bernoulli distribution. We'll talk about a binomial distribution. Though there are too many in number, we'll talk at least the more important ones. We'll see what is a Poisson distribution, which all come under the category of discrete distribution. And then we will enter into a few continuous distribution, where we'll talk about the more heavily used kind of a distribution, which is a normal distribution. We'll talk about different properties associated with the normal distribution. Another distribution which is heavily used in the world of finance and risk management, log normal distribution. So we'll discuss these two. Then we'll go with the concept of central limit theorem, one of the key aspects in the world of statistics. So, how do we really look at the central limit theorem? So, that is one more aspect we'll be focusing on. And another important aspect we will be talking about is the chi-square distribution, some other distributions where we look at the chi-squared. Then I'll talk about the t distribution. Then we'll talk about the f distribution, other distributions which have a few important derivations or important applications when it comes to the central limit theorem, and a few other distributions like triangular distribution is also used for triangular, the beta, especially where they have some kind of intervals, boundaries. And we will then towards the end look at the different mixture distributions combining two or more. So these are the different aspects we will be looking at in this session. So slightly a longer session, so it's better that we go with it step by step. So all these things, what do we really mean by a distribution? We know what are random variables. Now, and we also know that the random variables follow some kind of patterns, some kind of shapes. These patterns are typically called as distribution. Right? What are the possible values associated with a random variable? And what we are doing in this session is those kind of patterns which are more commonly observed and which have namings and which have a lot of utility in the world of risk management. So those are the ones we would be discussing of. Now, the first thing, the distributions typically need to be understood whether they are parametric or non-parametric. Parametric is something where there is a mathematical formula. Right? If the probabilities follow a kind of a mathematical formula or a function, we call them as parametric. Almost all the ones with names, whether I call uniform, normal, log normal, everything where I have a name to it, we call them as parametric distribution. On the other side, when I am calling something as a non-parametric, there is no mathematical formula associated with it. So it's just a collection of data, collection of the returns. It's a non-parametric. And to a large extent, if I have to really compare between them, parametric distributions are really easy to work with because I'm generalizing the pattern of my random variable. But at the same time, it may not be a reflection of the reality of the data because I am assuming that my data is following this kind of a pattern. So may or may not be supported with the real world data. Real world data may be forcibly be fitted into the into this distribution, but at the same time it helps me to generalize a lot of things to make conclusions in a much effective manner. Whereas when I talk about the non-distributed, non-parametric kind of distribution, I can very well think of fitting the data very well because it is exclusive to that particular data, but it is more and more specific. It can't be generalized. So I cannot make some kind of general conclusions from the data when I'm going with non-parametric kind of distribution. So whatever are the names that we are studying, all these names are associated with the parametric distributions only. So to start with, we will go one by one. So initially we'll look at what is a uniform distribution. Now, just to recollect, the probability for any continuous random variable, the probability that x lies between a and b, we have simply called it as integration between a and b, the probability density function. This is what is the probability that x takes the value between a and b. Now, here is where we'll try to bring in the pattern. In case of uniform distribution, which is the most basic distribution, which has so many applications to other distribution, the probability density function is equal to some constant k if x is lying between a and b, and it is equal to 0 if x does not lie between a and b otherwise. So we are simply saying the probability density function is constant equal to some k if x is lying between a and b, and the probability density function is 0 in all the other aspects. Which means if I am trying to plot a kind of a probability density function, let's say I have a here, I have a b here, so there is a k here. So my probability density function is more like this, right? Anything below a, it's 0. Anything above a is 0. And between a and b, it's constant. So from here, I can very well find out what is the value of that constant k, right? Because I know across, so from the minimum value to the maximum value, some k times f of x dx should be equal to 1, right? K times f of x dx should be equal to 1. So here, because now f of x is simply k, so k dx. So obviously it is kx times, I'm integrating between b and a, so becomes k times b minus a equal to 1. K becomes 1 by b minus a. So the constant typically becomes 1 by b minus a, which is the difference between the upper boundary and the lower boundary. So this is what is the uniform distribution all about. The graph. And this is the graph of the PDF. The probability of any outcome that is occurring should be equal to 1. So which means the area under this PDF is equal to 1. So based on this, I know that the constant should be equal to 1 by B minus A. Okay. Now I know that the constant is 1 by B minus A. Now for this uniform distribution, let me see if I can find out the mean. I know what is the formula for the mean. I am integrating it between A and B. F of x. Now I got the density function is constant 1 by B minus A. That is f of x. Right? 1 by B minus. And if I want to find the mean, I have to multiply it with x. So I'll get it as 1 by B minus A times x squared by 2. B and A. 1 by B minus A times B squared by 2 minus A squared by 2. B squared minus A squared by 2. So then it is becoming A plus B by 2. So the mean is coming out as A plus B by 2, which is the average of the minimum and the maximum values. So that's the way we are computing the mean. If I want to compute the variance, okay, A to B, f of x, x minus the mean, x minus of mean is A plus B by 2. Right, x minus A plus B by 2 times the mean. Now this is where I can very well work it out. Right, so I'll take out 1 by B minus A out. Now x is x squared by 2 minus A plus B by 2 is nothing but A plus B by 2 times x. This I am integrating between B and A. So it becomes 1 by B minus A out, B squared by 2 minus A plus B by 2 times B minus of A squared by 2 minus A plus B by 2 times A. Let's simplify this. 1 by B minus A into, okay, B squared by 2 minus AB by 2 minus B squared by 2 minus A squared by 2 plus A squared by 2 plus A B by 2. Okay, so these are completely somewhere we have messed up the stuff. The variance, if I'm looking at the variance, I'm integrating it between A and B. 1 by B minus A times x minus mean whole square. So let me take it as mean itself, then we'll substitute it later. So I'll take it as 1 by B minus A times integration A to B x squared minus 2 mu x plus mu squared. Let me do it step by step. Okay, 1 by B minus A times x cube by 3. So which is B cube minus A cube by 3 minus 2 mu times x squared by 2, which is B squared minus A squared by 2 plus mu squared times x B minus A. So yeah, now it is coming out. Now I have 1 by B minus A. So if I take out B minus A out, B squared plus AB plus A squared by 3. So B minus A I am taking out so that I can take them out. minus 2 mu is a plus b by 2 times, I've taken out b minus a. So this is b plus a by 2 plus mu squared a plus b by 2 squared, b minus a I have taken out. So this is what is left altogether, right? A squared plus ab plus b squared by 3. So if I look at it, minus of a squared plus 2ab plus b squared by 2 plus a squared plus 2ab plus b squared by 4. Now when I take the LCM, it comes to be 4, giving me 4a squared plus 4ab plus 4b squared minus 6a squared minus 12ab minus 6b squared plus 4. So it is 3a squared plus 6ab plus 6b squared. This is what is coming out overall. So which means I can take out 6b squared from it. Then I have 7a squared minus 6a squared, making it a squared. Then I have 10ab minus 12ab, making it minus 2ab. Then I have 4b squared minus 3b squared, which is giving me b squared. So it is coming out to be something like this. So which is giving me b minus a whole squared by 12. So I'm getting b minus a whole squared by 12 as the variance, a plus b by 2 as the mean of this uniform distribution. And obviously if I'm setting a equal to 0 and b equal to 1, so the entire thing is lying between 0 and 1. In this case, this uniform distribution is called as the standard uniform distribution. Very, very extremely common kind of distribution where the random number generators, which are the basis for Monte Carlo simulation and various applications, they are based on the standard uniform distribution itself. So the standard uniform distribution really plays a very important role as a building block for building various computer models in the world of finance and risk management. Now, the other important aspect is how do I get the CDF for this uniform distribution? So obvious, I'll take between a and x. C I know 1 by b minus a times dx. So it is coming out as 1 by b minus a times x, which is nothing but x minus a. X minus a by b minus a is what is the cumulative distribution function p of x less than or equal to x is x minus a by b minus a. That's how we are getting the cumulative distribution function by integrating the probability density function. So when we are saying when x equal to a, the cumulative distribution function is 0, we are at the minimum. And when x equal to b, we are at the maximum, so the cumulative distribution function is coming out to be 1. And for any intermediate value also, we can quite comfortably find it out. So that's what is coming as a part of the basic understanding of the uniform distribution. Now, let's move further to the next one where we'll try to understand the Bernoulli distribution. Right. Now, what is this Bernoulli distribution? It is basically whenever we are talking about any random variable which is a Bernoulli random variable, it takes two values. 0 or 1, success or failure. So the probability of occurring of this is P. The probability of occurrence of this is 1 minus P. So that kind of a variable is what we call as a Bernoulli random variable. So its value is either 0 or 1. The probability P is that value of the variable is equal to 1. So which means the probability of x equal to 1, if I say it's P, probability of x equal to 0 is nothing but 1 minus P. Now based on that I can find out what is the mean. Mean is what? Probability times the value. P times 1 plus 1 minus P times 0, which is P. Then what is the variance? In variance also we are finding out the same way. X minus mu whole square times the probability. Okay, probability is P times x minus mu whole square. 1 minus x is 1 minus P whole squared plus 1 minus P times 0 minus P whole square. So what is it coming out? Variance is coming out as P into 1 minus P squared plus P squared times 1 minus P. Probably something gets simplified. Let's see. So I'll take 1 minus P out. So P into 1 minus P. P minus P squared plus P squared. Wow. P squared is going out, so it is coming out as P into 1 minus P. So the variance of the Bernoulli distribution is P into 1 minus P. The mean of the Bernoulli distribution is P. So especially the usage wise, when there are binary outcomes, only two possibilities, that is where we are using the Bernoulli distribution. So the binary outcomes are very common in the world of finance and risk management. We talk about, let's say, a bond, default or non-default, stock returns, positive or negative, right? So government or central bank raises the interest rates, do not raise the interest rates. These are different kinds of scenarios where a Bernoulli distribution can come into picture. So if I am more interested in a Bernoulli variable simulation, so I'll start with a standard uniform distribution variable itself. I know standard uniform distribution variable value will lie between 0 and 1. So I'll generate some random number between 0 and 1. And if at all I say that there is a 60% probability that I'll get a 1 and 40% chance that I'll get a 0, I'll generate a random variable. If it is less than 0.6, I'll associate it to 1. If it is greater than 0.6, I'll associate it with a 0. So that's how I can very well generate the random variables with following a particular Bernoulli distribution also. Right? All right. Then we move to the next one. Next common kind of a distribution, which is a binomial distribution. Probably it can be thought of as the collection of the Bernoulli random variables. So Bernoulli random variable is something that it takes just 0 and 1. A collection of such kind of random variables is what is a binomial. So I can very well think of the same Bernoulli variable task being performed n times, right? N such variables are collected and each one is independent of the other. Then it boils down to a binomial distribution, right? So if I'm talking just for an example, n bonds are there, n number of bonds are there, and I'm saying 10% is the probability of default for each bond. right? Some probability. P is the probability that each bond will default and none of the bonds are interrelated, they are independent. Then if I'm talking about some X number of bonds defaulting out of the N, is the typical way in which any X of them can default is NCX. Out of N, some X number of bonds defaulting, any combination of X number of bonds defaulting is coming out as NCX different possibility. And if the probability of one bond defaulting is P, non-defaulting is 1 minus P. So if X bonds are defaulting, the probability is P to the power of X. By using the independent events, I can find the probability of X bonds defaulting is this much, and the probability of 1 minus X bonds, N minus X bonds not defaulting is 1 minus P times N minus X. So that is how we get, this is the probability density function that is associated with the binomial distribution. The probability that X bonds will default at any point in time is given by this kind of a function, right? So this is the probability density function for a binomial distribution. So we can talk about out of the 5 bonds. So we'll take one simple example to try to understand that. So if I assume that the probability of default of one single bond is 10%, then the probability of not default is around 90%. Let's say I have 5 bonds. The number of bonds is 10. There are 10 bonds. Now I really want to know what is the probability of 0 bonds defaulting, 1 bond defaulting. So I really want to know what is the probability associated with all of them. So this is where I can say probability of 0 bonds defaulting. So I am saying my NCX. This is my NCX times probability of default P to the power X times 1 minus P. This is my 1 minus P to the power N minus X. N minus X. So which is giving me that there is a 34.86% chance that none of the bonds are going to default. Similarly, there is a 38% chance that one of the bonds is defaulting, 19.3% chance that two of them are going to default, 5.7% chance that three of them are going to default, and so on. Probably there is a very, very limited chance that 7 and above are going to default. Very, very almost close to 0. Even for 6, it's just 0.01%. So this is the kind of a probability density function. I add up all of them, it is going to be exactly 100%. So this is what is the probability. So probably if I am talking about the mode of this distribution, I'll say it is equivalent to 1 because the one that is coming out with the highest frequency. So the highest probability of occurrence is associated with this particular number of defaults. So that's the reason we are saying this is the mode. So the mean of the random variable, if I'm looking at, okay, the mean of this particular random variable, either I can find out the sum product. To find out the mean, it is nothing but the value multiplied by the corresponding probabilities. So I'll say the value multiplied by the corresponding probabilities, which is going to come out as 1, which in other case the mean is nothing but NP. N is the total number, which is 10. and P is the probability of the event occurring, which is 10%. So that's the reason the mean is coming out to be around 1. And when we are talking about the variance, just as a thing to remember, the variance in case of a binomial distribution is NP times 1 minus P, which is nothing but the mean times 1 minus P is the variance that is associated, right? So even in this case, I can find out the variance, which is nothing but N P times 1 minus P. 0.9 is the variance, and around 1 is the mean for this particular distribution. And from here, I can find out the standard deviation, which is the square root of the variance. So 0.94 happens to be the standard deviation of this particular distribution. Probably if required, we can derive that as well. So we'll take each observation minus the mean. Each observation minus the mean, square it. Each observation minus the mean, we are squaring it. That's the first thing. We are multiplying it with the corresponding probabilities. So I'll do a sum product between these probabilities and the differences, which is giving me that my variance is 0.9 and the standard deviation is nothing but the square root of this variation. Now let's observe some kind. Let's try to give some kind of graphs here, right? Probably let me put a graph. Let's say I'll put a simple column graph, right? And let's say where the gap does not exist at all. So I'll remove the gap. So let's say this is the kind of a distribution that is coming when P is 10%. Now, if I make, so this is looking more and more right skewed. But if I make P as 50%, it comes more and more symmetric. You see the graph is coming more and more symmetric when I am doing a P as 50%. And let's say if I am changing N to some other number, so everywhere when P is close to 50%, I am seeing more and more of normal kind of or symmetric kind of a distribution, right? When I'm saying P is 10, it is going like this. Now, if I increase, let's say I say P is 30, right? I say P is 30 and probably let me increase this thing up to 30, right? Let me just increase this thing up to 30. All right, when I'm increasing this up to 30, I could clearly see again if I'm doing the plot. Now again I have to do the plot by taking all these values. I'll do the plot by considering all these values again. It should come closer and closer to a normal kind of a distribution. So a binomial distribution, if it is increasing more and more number of, if n is getting more and more higher, we see that with a probability of 0.5 or 50%, I see that the distribution is coming closer and closer to the normal. And generally the mode is n by 2. If at all my n is even, my mode is n by 2. If n is odd, I see that the mode is that particular whole number that is on either side of n by 2. So if n is 5, then my mode will be 2 and 3. There are bimodal. 2.5 is n by 2. My mode will be on either side of n by 2. right? So that is what constitutes a binomial distribution, which we really need to be slightly comfortable with. Now that we are done with the binomial distribution, let's move on to the next important distribution, which is the Poisson distribution. And for a random variable x, the Poisson distribution simply says that the probability that x is equal to some n is nothing but e to the power of minus lambda, lambda per n divided by n factorial. This is what is the probability of x equal to n for some value lambda. Right, so let's take the same. So I'll call this as binomial, whereas I'll take one more data set where I'm calling it as Poisson. So let me take some lambda, right? I'll take this as Poisson. Here I'm taking some value of lambda, let's say to be around 0.5. Then, right, or probably let me call lambda is 1. And for this, I really want to find out if what is the probability of 0, 1 occurrence of all these values. So let's say I want to do it for up to 15. So what is that we are saying? These are x. So e to the power of minus lambda times lambda power x, right, divided by factorial of x. So this is what is coming out as the probability of getting a 0, 1, 2, 3 and so on. The summation is almost 100% again, right? If lambda is 1 and it is following a Poisson distribution, I could see that the graph is going to work out more like this. After a certain point, it's almost zeros, right? So this is what for different values of x, we can really see what is going to be the distribution. Like if I'm putting lambda equal to 2, my distribution is coming more like this. If lambda is becoming 4, my distribution is coming more like this. And if my distribution is 6, my lambda is are probably for 6 it's coming more like this, and for 8 it's coming even more like this. Now what is that I'm seeing? As lambda is increasing, I'm seeing some kind of a normality coming into the shape as well here. So this is how the Poisson distribution is being represented. I'm just trying to understand some of the conceptual aspects behind the Poisson distribution. Especially, it is used for modeling the occurrence of events over a period of time. So if I really want to find out number of bond defaults during a specific time period, or probably if I want to model the number of crashes in the stock markets, so I'm modeling n number of events that occur in a particular interval of time. And lambda, now the good thing or interesting thing about the Poisson distribution is the mean is lambda, even the variance is also lambda. So the standard deviation will be square root of lambda, right? So what we are simply trying to say is it is generally used for modeling the number of events within a particular time interval, where lambda is the expected number of events in that particular interval. So generally for modeling the jumps, in a jump diffusion models, we use the Poisson distribution itself. Now, here is where another related term comes into picture, which is called as a Poisson process. What is this Poisson process all about? See, if I am talking about the rate at which the event is going to occur over time, if I am assuming that is some constant, and the probability of any one event occurring is independent of all the other events, then in a time period t, if I really want to find out what is the probability of some n number of events occurring, we will take it as, see, lambda is the rate at which in a interval, in a unit interval of time, lambda is the rate at which the events are occurring. So during a period of t, lambda t events are going to occur. So even that is going to follow a Poisson distribution, where so the probability of x equal to n will come out as e power minus lambda t power n by n factorial. And where t is the time elapsed, expected number of events before the time t is becoming the lambda t. Then the probability that n number of events will be generated is simply given by this formula. Just as a quick example to understand it, right? If I'm seeing that a bond portfolio is there, and the defaults in this bond portfolio, I came to know that they are following a Poisson process. So each month, so I'm finding over a time period, over 1 month, I'm assuming that there are around 4 defaults per month. Now, what is the probability that there are exactly 3 defaults in a month? So the lambda is 4 per month. T is 1 month. So lambda t is 4. Now I can very well follow the Poisson process, and I say probability of x equal to 3 is e to the power of minus lambda t power x divided by x factorial. So I can work it out. And if someone says no, over 2 months, what is the probability of exactly 3 defaults? So again, in that case, t will be 2 months, lambda t will become 8. Everything else is the same. Probability of x equal to 3 will become e to the power of minus 8 cubed divided by 3 factorial. So this will give me a different probability of occurrence of 3 defaults over a period of 2 months if the Poisson process, if the probability if the lambda is around 4 per month. So that is how we can work out with the Poisson process. Then, once we know something about the Poisson distribution, then we'll move towards the continuous distributions, wherein the more important distribution that we are bringing in that context is the normal distribution. Very, very heavily used distribution in the world of statistics, and it has lots of applications in the world of finance and risk management. Right? So there is a lot to understand regarding this concept of normal distribution. In general literature, the shape of the normal distribution, we talk about it as a bell curve. So the probability density function associated with the normal distribution will come more with this kind of a shape. That's the reason we are calling it as a bell curve. So a few things. The probability density function, I'm seeing that it is symmetrical, which means the skewness is 0. And to a large extent, because it is symmetrical, we see that the mean is equal to median is equal to mode. And a few other properties. The kurtosis of a normal distribution is 3, which means the excess kurtosis is always 0. Some of the important characteristics associated with a normal distribution. Conceptually, it is in some fields, it's also called as a Gaussian distribution. Right? The names can interchangeably be used. When I'm saying a Gaussian distribution, it is nothing but it's a normal distribution. Now come some of the interesting formulas. When I'm talking about the probability density function, it works out as 1 by sigma root 2 pi e to the power of minus half x minus mu by sigma whole square. This is what will work out as a normal distribution function's probability density function, where mu is the mean and the sigma is the standard deviation. So that's the reason generally the standard normal distribution is always defined. X follows a normal distribution with a mean mu and variance sigma squared. That's a typical way of defining a normal distribution. And that's the reason in some of the books you will always find normal distribution is always defined by its mean and variance. Because here you could see only those two things sufficient to describe the normal distribution value. So let's try to generate some kind of a normal distribution using these numbers. Right, let's take mean is 0 and standard deviation, let me take it as 1. And right from, let's say I'll generate for very small values, minus 3, minus 2.95. I'll go with this kind of a gap. Let's say up to plus 3 is what I would like to generate. So I'm taking different values of x. These are the different values of x I am considering. And corresponding to these values of x, I am interested in looking at the density function. 1 by sigma times square root of 2 pi, right? 1 by sigma square root of 2 pi multiplied by e to the power of minus half x minus mu, x minus mu x minus mu by sigma squared minus 0.5 times x minus mu by sigma squared. So this is what is coming out, and finally I replicate it. So some different values are being bound to come up. And now what I can do is I'll try to do a small graph associated with these values. Oh, a perfect normal distribution curve is getting generated. That is how I can replicate a normal distribution curve. So probably if required, you change the mean and the standard deviation. Does not matter. Right? The only thing is now you may have to increase the observations even more further. Right? The mean is 0. So you are seeing. So you just need to change the pattern of the data. I mean the x-axis, where you will definitely find different observations coming up. And it will come in the shape of a bell like this always. So x is normally distributed with a mean of mu and variance of sigma square. Now, coming to some of the important properties associated with the normal distribution, any linear combination, of independent normal variables, any linear combination of independent normal variables is also normal. So if I'm saying x is a normal variable and y is a normal variable and x and y are independent, so if I'm talking of z which is ax plus by, even this is also a normal variable. The only thing is this will have a mean of a times mu x plus b times mu y, and the variance of it will become a times the variance, a squared times the variance of x plus b squared times the variance of y, but it will still be a normal variable itself. This is a very interesting aspect for us to understand. So we can very well consider that the log returns, the logarithmic returns of the stocks, they are typically IIDs, independent and identically distributed, and you find that they are normally distributed. So which means even the average, even their average also will be normally distributed. And if I'm looking at the density function, if I'm saying mu is 0 and sigma is 1, I call this as a standard normal variable. And for a standard normal variable, here if you look at it, comes 1 by root 2 pi, sigma is 1, e to the power of minus half x squared. So this would be the typical probability density function associated with a standard normal distribution. So for a standard normal distribution, probability density function will represent it with this letter phi, whereas the capital version of it is what will be for the cumulative distribution function associated with the standard normal distribution. And this cumulative distribution function, we don't have a direct function, but we have a tabular kind of representations which can help in terms of identifying the cumulative distribution function, and there are lots and lots of applications of the cumulative distribution function in the world of finance and risk management. So a standard normal variable can very well be converted into a regular normal variable with a mean of mu and variance of sigma squared. How do I convert it? I take the mean plus sigma times the standard normal variable is what I can consider, which will make my distribution more or less having a mean of mu and a variance of sigma squared. And similarly, I can even go ahead in terms of creating the correlated normal variables also. By default, the normal variables may be independent. So I can even create correlated normal variables also. If I'm talking about x1, x2, x3 being three normal variables, and I want to generate xa and xb, which have the correlation of rho between them. The simple way for me is I take one of these, let's say x1, I give a weightage of rho, square root of rho to it. And the remaining, which is 1 minus rho squared under root, I give it to the random part x2, and here I give it to the random part x3. In this case, we see that the correlation between them exactly is rho itself. So the standard normal variables, I can convert them into those variables which have a correlation of rho in between them. We'll look at this aspect in much more detail in our chapter of Monte Carlo simulations, which we are going to take up at a later point in time. So the normal distributions have a lot of applications in finance and risk management, especially when I'm talking about the log returns. We are using it much more heavily there, right? We are using them using the normal distributions itself. And the reason is, if you look at the typical traditional return, if the price today is 100, the price becoming 0 is like 100% fall. So if I take the regular return, the value is just between -1 and infinite. But when I'm taking the log returns, literally it could be between minus infinite to infinite, which is what is the scope of a normal distribution. So I can't take the returns to follow a normal distribution, but it is much more appropriate for me to consider the logarithmic returns following a normal distribution. And if we look at the real applications of the normal distributed log returns, we see in very many simulations, a lot of Monte Carlo simulations talk about the normally distributed log returns. When we talk about the Black-Scholes option pricing formula, which is one of the heavily used one for option pricing, even that assumes that the log returns follow a normal distribution. So you can think of a wide number of applications which assume that the log returns follow a normal distribution. But if I have to find the cumulative distribution function for the normal distribution, there is no direct formula that is available. But there are so many statistical packages which are comfortable in terms of finding out the cumulative distribution function, because majority of the time they find through various numerical procedures. Numerical methods, numerical procedures, numerical algorithms are generally used for solving the cumulative distribution function associated with the normal distribution. But apart from that, a few more interesting points associated with the normal distribution is, if a particular random variable is following a normal distribution, approximately 68% of the observations will fall within plus or minus 1 standard deviation of the mean. And approximately 95% of the values lie between plus or minus 1.96 standard deviations from the mean. And almost 10 or 90% of the values lie between plus or minus 1.64 standard deviations from the mean to 99% of the observations lie between plus or minus 2.58 standard deviations from the mean. So these are some of the important rough numbers which talk about what percentage of the observations fall within how many standard deviations from the mean. Remember, this kind of remembrance is needed only for a normal distribution and not for others, because normal distribution had quite a good number of applications compared to the other distributions, right? So some of the important numbers like this are very much worth enough to understand associated with the normal distribution. All right. So whenever we move, whenever the need comes, we'll use the remaining concepts associated with the normal distribution wherever applicable. But at least these important points should be kept in mind with respect to the normal distribution. All right. Then the next important distribution that I am covering right now is the log normal distribution. As simple as we have been talking about the log returns. They are following a normal distribution. Then in some form the returns should be following some other distribution. Now this is where we came to know that 1 plus returns, they follow a log normal distribution. In general, if logarithm of values follow a normal distribution, the original values follow a log normal distribution. Right? That's a simple way to understand and link these two. So if the log returns are normally distributed, generally the standard returns, in this case, a special case, 1 plus standard returns, they follow a log normal distribution. But in general, if a particular value follows a log normal distribution, the logarithm of those values is expected to follow a normal distribution, right? And adding a constant to a value will not alter the shape of the distribution. So which means 1 plus standard returns also follows a log normal distribution itself. And if you look at the density function, hardly any difference. The only thing is, instead of 1 by sigma root 2 pi, we also have one x out here, e to the power of minus half x minus mu by sigma whole squared. We write it as log x minus mu by sigma whole squared. This is the density function that is associated with a log normal distribution. So if a particular variable has a log normal distribution, then I can very well say that the logarithm of that particular variable is having a normal distribution. So simply put, if the log returns are normally distributed, then 1 plus standard returns are log normally distributed. And typically, because see, log normal distribution actually lies between 0 and infinite. But the standard returns, they lie between -1 and infinite, minus 100% to infinite. That's the reason we are considering 1 plus returns, 1 plus standard returns, so that it also lies between 0 to infinite, and I can map it with the log normal returns. That's the reason we are saying 1 plus returns follow a log normal distribution, because a log normal distribution value, they lie between 0 and infinite. And the density function looks more and more similar to that of a normal distribution, where x is replaced by log x. Now let's try to find out the mean associated with this kind of a distribution, right? If I'm able to write it in form of x minus mu kind of stuff, then it is like I'm able to find the mean of the distribution. So let's try targeting it. So f of x 1 by x sigma root 2 pi e to the power of minus half log x minus mu by sigma whole square. So let me say log x, let me take it as y. Right, just for understanding, I'll put log x is y, which means x is e to the power of y. So I'll call 1 by x is e to the power of y sigma root 2 pi to the power of minus half y minus mu by sigma whole square. So it comes out as e to the power of minus y by sigma root 2 pi e to the power of minus half y minus mu by sigma whole square. Now, even this I have to take it inside. So if I'm taking this also inside, if and so it becomes 1 by sigma root 2 pi e to the power of minus half. If I am taking this y also, minus y minus half y. So it is becoming e to the power of minus half. So this is becoming minus y minus y squared plus 2 mu y minus mu squared by sigma. 1 by sigma root 2 pi e to the power of minus half. I have to write this entire thing if I write it as y minus of mu plus half sigma squared by sigma whole squared. So it is coming y squared minus mu squared. Then it is coming 2 mu and it is half sigma squared. So 2y times mu plus half sigma squared is coming to 2y mu, and this is 2y which is mu sigma squared, and it is also coming out as the sigma squared is cutting up. So overall it is coming out as the mu that is coming through this procedure, the expected value of x is e to the power of mu plus half sigma squared. So if I am substituting, if I am using a log normal distribution, it is primarily, it is symmetrical around mu, and the peak is e to the power of mu minus sigma squared. The expected value of this is coming out as e to the power of mu plus half sigma squared. That is the expected value of the log normal distribution. And if I want to really look at the variance of the log normal distribution, it works out as e to the, so if this is the mean, the square of it, mean squared, which is e to the power of 2 mu plus sigma squared times e to the power of sigma squared minus 1. This is what will come out as the variance of the log normal distribution. So the mean of the log normal distribution is e to the power of mu plus half sigma squared, where mu is the mean of the original log normal distribution, which is the original underlying normal distribution. Sigma squared is the variance of the underlying normal distribution, whereas the variance comes out as mean squared times e to the power of sigma squared minus 1, or it is nothing but e to the power of 2 mu plus sigma squared times e to the power of sigma squared minus 1. So this comes out to be the variance of the log normal distribution. And because of this relationship, we will also define one more relation, which is the log normal returns is nothing but the standard return minus half the square of the standard return. If R, capital R is the standard return and the small r is the corresponding log return, then this is how we find the relationship between these two. And so typically we need to understand the mean and the variance of the underlying log normal distribution as well. And depending on the need, we can go ahead working directly with the normal distribution, assuming the log returns following a normal distribution, or we can directly keep working with the log normal distributed values itself. All right. Now that we have looked at a few distributions, the next thing that we are going to understand is the concept of central limit theorem. So for that, let me give you a small instance. Let's say we have good number of equity stocks, right? And I want to really assume that the different constituents, let's say I'm talking about the index, and here I want to really assume that the constituents of that particular index, they are IIDs, though in reality they are not, but let's assume that they are IIDs, which means they have identically distributed and they are uncorrelated with each other, right? Then we are simply talking about, I can look at the distribution of the entire set of index rather than looking at each of the individual distribution. If each of the elements is IID, we can say a lot regarding the distribution of the entire population, even if the distributions of the individual elements, which are the constituents, is literally not known. See, simply put, if x is a normal variable and y is a normal variable and both of them are IIDs, then x plus y is also a normally distributed variable, right? Similarly, if x is a uniform distribution and y is a uniform distribution, then x plus y can result in a triangular kind of a distribution. So different values, whatever are the different individual variables, we can see that if I typically do some kind of operation on them, linear operations on them, I could see that even they follow some kind of a distribution. But in this case, what we see is, okay, instead of x, y, z, and so on, so many observations if I add up. So let's say x, y, each one of them, I don't know what is their distribution, but I say that they are IIDs. They all follow a similar kind of a distribution and they are independent of each other. And there are some n such kind of variables. What we say is, if I add all of them together, the interesting part is the summation, it converges to a normal distribution. Very, very interesting aspect. Let's assume x1, x2, so on, xn. I don't know what is the x1, x2, so on, xn. Whatever is the distribution associated with that xi, I'm not much bothered. The only thing I know is they are IIDs. They are independent and identically distributed. And n is very, very large. Then what we say is, if I sum up all of them, x1 plus x2 plus xn, this sum is going to converge to a normal distribution. Extraordinary a piece of information where lots of statistical analysis is purely based on, right? So even if I take a big set of uniform variables, right, for that the better way to look at is, let me try simulating that stuff, right? Let me take some uniform distributed values. So for that I'll use a random variable, a rand. So let me say that I have some some 52 such kind of random values, right? And I have generated different possibilities. Let's say I'm talking about a few thousands. Well, I'll explain it in much detail when we are doing the simulation. But let's say I am talking about 50 variables, 52 variables, x1, x2, so on up to x52, right? And each one, so assume that these each column is a random, each column, sorry. So let's talk about this being x1, x2, x3. So x1 is following a normal uniform distribution between 0 and 1. x2 is following a uniform, x3 is following a uniform. Now, and it could be any other as well, but they are all identical. Now I am taking the summation. Okay, the summation, this is the summation. All right, so this is the sum across. Now what we are saying, this summation, it should follow and it should approximate a normal distribution. How do I know if it is a normal distribution? I can check the skewness. I'll check the skewness of this data. It's very close to 0. I can look out for the excess kurtosis of this data. Even that should be pretty much close to 0. So these two are pretty much close to 0, which is an indication that the summation is a normal distribution. This is what is an important relationship. If n is large, here n is 52, and the individual observations, they are following some kind of a distribution. But whatever is that kind of a distribution they are following, as long as they are IIDs, their summation will follow a normal distribution. Right? So as we add more and more variables, the distribution converges to a normal distribution. It's just not with uniform distribution. It can apply to any distribution, which means my x1, x2, so on can follow any distribution, but they all should be IIDs. In that case, the summation of x1, x2, xn will approximate a normal distribution. Even their average also will approximate a normal distribution. Very interesting result, which is the a very interesting result, which is what is called as a central limit theorem. So the summation, if each one is a normal distribution, the sum, or if each one is any distribution, the summation Sn is going to follow a normal distribution with a mean of n times mu and with a variance of n times sigma square. Now here n was 26, 52, and we know for a uniform distribution the mean is 0.5. So if I try to find the mean of this, it should be to somewhere around 26. The mean of this is 26.01. And even if I am looking at the variance, it is nothing but n times sigma squared, 52 times. What is the variance of a uniform distribution? It is b minus a whole squared by 12. So it is 1 by 12. 1 by 12 times 52. So I should get it somewhere just above 4 is what should be my variance. So if I look at the variance, it's 4.32. So which is coming out more and more similar to that of a normal distribution. So that's the same way the average of n numbers also is going to follow a normal distribution with a mean mu and variance sigma squared by n. So this is what is going to happen to the average as well as to the mean, but provided n is pretty much large. So in a simple way to put it, as n approaches infinite, the sum of a set of variables, set of IIDs converges to a normal distribution. It's an important result in the world of statistics, and that is what makes a normal distribution more and more important to be understood. Right? So, in many cases in the world of risk management, finance, we have the data where we assume that they are IIDs, or in reality they are IIDs itself. Then we can very well use the central limit theorem, which can help us to derive various other statistical properties as well, right? So so typically I can look at the mean of a sampling distribution following a normal distribution with a mean mu and a variance equal to sigma squared by n. Summation follows a normal distribution with a mean n mu and a variance n sigma squared, right? And typically lots and lots of applications are created under the usage of the central limit theorem itself. All right. Then we will move to our next concept where we try to understand a chi-square distribution. Now from here onwards, some more interesting stuff. So let's look at our standard normal variables. Let's assume that I have Z1, Z2, Zn. So I had n number of standard normal variables. What are these standard normal? They have a mean of 0 and a variance of 1. Then their squares, Z1 squared, Z2 squared, so on, summation of Zn squared, which is nothing but sigma Zi squared. This one is following what is called as a chi-square distribution with n degrees of freedom. That's the simple way to work out. So if I am saying Z1, Z2, Z3, so on, Zn are standard normal random variables, then the sum of their squares will follow a chi-square distribution with n degrees of freedom. So if there is S1 with k1 degrees of freedom and S2 with k2 degrees of freedom, then S1 plus S2 will also be a chi-square distribution with k1 plus k2 degrees of freedom. And a few things, because chi-squared is associated with the summation of the squares, chi-square distribution is always non-negative as few properties. And it is also not symmetrical, because the square of a particular distribution cannot be a square of a symmetrical distribution cannot be symmetrical. So it is more asymmetrical, and what we see is it is more and more positively skewed. As a relation, it is more and more positively skewed, right? Probably let's try generating it. So let me use some standard normal variables. I can use a norms inverse kind of a function, right, for generating a standard normal variable. Okay, so these are the different standard normal variables. Okay, let me take 10 of them. Right, these are the different standard normal variables. I am generating them. So this is what is actually Monte Carlo simulation all about. But I'll talk about these things at a later point when we are covering simulation. Okay, so these are the individual standard normal variables. Now, if required, actually I can do their squaring. Right, so I'll do the squaring of these standard normal variables. Alright, I have squared all these standard normal variables, and now I want to sum them up. Sum of the squares of the standard normal variables, this is the possible value. Now what we say is this is not normal. Let me try. If this is normal, I'll take the skewness. The skewness is positive here, 0.87. And kurtosis is also positive, 1.22. So that's the reason we see that it is a positively skewed kind of a distribution and it is a chi-square distribution, right? So we can understand that it is a chi-square distribution, and the mean of this chi-square distribution is k. Let's try finding out what is the mean. The average 9.93. We had 10 observations. So the mean is coming out to close to 10. So mean is close to k and the variance of it is 2k. So the variance should come out as 20 approximately. For this distribution, the variance should come out to 20. So you see it's very much closer to 20. So as k is increasing, the chi-square, so instead of 10, if I do it 20, 100, infinite, as k is increasing. So typically for a chi-square distribution, some of the properties, the mean of the chi-square distribution is k, which is the same as degrees of freedom. The variance of this chi-square distribution is 2k, which is twice the degrees of freedom. And as k is increasing, the chi-square distribution becomes more and more symmetrical, but initially it is nowhere symmetrical. Right? Probably if I'm trying out, let's see how the pivot table for the same is copying up. So I could see the numbers coming more from this perspective, wherein I can very well group them so that I can plot a pivot. So you could see the distribution more coming in this kind of a fashion, which is coming out as a positively skewed kind of a distribution, right? So that is what is happening with a chi-square distribution. As k is increasing, the chi-square distribution becomes more and more symmetrical. And if the k is coming more and more closer to infinite, k is tending to infinite, again this also happens in such a way that the chi-square distribution is also converging to a normal distribution. Of course, even for a chi-square distribution, there is a density function, there is a distribution function. Probably just for the sake of knowing them, the density function associated with a chi-square distribution is nothing but 1 by 2 to the power of k by 2 gamma times k by 2 multiplied by x to the power of k by 2 minus 1 e to the power of minus x by 2, where the gamma function is nothing but it's an integration from 0 to infinite x to the power of n minus 1 times e to the power of minus x dx. So typically we don't need to remember all this stuff. We need to understand the pattern of the distribution and the data. So the chi-square distribution is very heavily used in the risk management, especially when we talk about the hypothesis testing for the variances. We will use the chi-square distribution very heavily. So we just need to understand the properties associated with the chi-square distribution. So if I have to generate it, we can generate using the above density. We can probability density function taking the different values of k, which is the degrees of freedom. For different degrees of freedom, the shape of the chi-square distribution is going to come out in a different manner. On the same lines, we have two other distributions which are called as the student's t distribution and f distribution. Couple of extremely useful distributions in statistics and risk management, especially with the world of hypothesis testing. Now, the student's T is a very interesting one. Take Z, it's a combination of two distributions. Z, take it as a standard normal distribution, and U, take it as a chi-square distribution with k degrees of freedom. And these two are independent. Then X is something, generate a random variable, generate a variable which is Z divided by square root of U by K. And this X is what is supposed to follow a T distribution with K degrees of freedom. So the standard normal variable divided by the square root of the chi-square variable divided by its degrees of freedom is what is going to follow a T distribution with K degrees of freedom. The, the typical density function and the distribution function are quite complicated, but we really need to understand the pattern of the data. So if this is a normal distribution, what we see is a chi-square distribution will have a fat tail and it will have a small peak compared to a normal distribution for lesser degrees of freedom. So as the degrees of freedom increases, the chi is going, the T is going to approach a normal distribution. Until that time, its peak is going to be much lesser, but the tails are going to be much, much higher. So I really don't need to bother about the PDF and all for a T distribution, which is very much complicated. But I really need to understand what is the shape of this distribution and how it changes with the degrees of freedom. Typically, few important points. The T distribution is symmetrical around the mean, and the mean is 0 because we have taken the standard normal distribution in the numerator. Even the T distribution is symmetrical around the mean, which is 0. For if the K is very, very small, for K degrees of freedom, when K is very, very small, the T looks like a standard normal distribution itself, but the only thing is the tails will be much, much heavier, because I'll find that the kurtosis will be much, much higher. For the small values of K, the mean will be still somewhere around 0, symmetrical, but the kurtosis is much, much higher. But as the K is increasing, the kurtosis is coming closer and closer to 0. So when K is coming closer and closer to infinite, which is the number of degrees of freedom coming closer to infinite, I see that the T distribution is more or less converging a standard normal kind of a distribution. Very interesting point to remember. And when I look at the variance associated with a T distribution, it is nothing but K divided by K plus 2. K divided by K plus 2 is the variance of the T distribution. And if K is going more and more closer to infinite, I see that this is converging to 1. So that is what is a convergence to a standard normal distribution whose variance is equal to 1. And large number of users of the T distribution also lie in the world of hypothesis testing, especially for modeling the returns of financial assets. See, if I typically observe that the returns of the financial assets, they generally follow a T distribution, because I see them to display more and more of higher kurtosis. They may be symmetrical, but they display a higher kurtosis, which is an indication that they can't follow a normal distribution. They might be following a T distribution, right? Then moving forward to understand the F distribution. Here also, this is also a derived distribution. If I'm looking at U1 and U2, U1 is a chi-square distribution with K1 degrees of freedom. U2 is also a chi-square distribution with K2 degrees of freedom. Then if I define X as U1 by K1 divided by U2 by K2, this is what is going to follow an F distribution with K1 and K2 degrees of freedom. Right, so the F distribution will have these two parameters K1 and K2, and it is nothing but it's the ratio of two chi-square distributions. Again, I really don't need to get into the probability density function and distributions because they are very much complicated, so we don't need to get into the process of remembering the probability density function. You can simply Google out, or you can simply look out for any textbook. You will get the density functions associated with these two, either the T distribution or the F distribution, but they are very complicated to look at. So no one really wants to get into the memorizing of the aspect. But again, I need to have a good understanding of the shape of the distribution and some of the important properties that are associated with the distribution. And a few things. This is a ratio of two chi-square distributions. Chi-square is non-negative. So even the F distribution's density function also will not take any kind of negative values. And just as a few other results, the mean of a F distribution is nothing but K2 divided by K2 minus 2. And the variance is slightly complicated, 2K2 squared times K1 plus K2 minus 2 divided by K1 into K2 minus 2 squared into K2 minus 4. This is the value for the variance of the F distribution, and this is the mean of the F. But again, as I don't need to memorize all these things, but as some of the important processes, if K1 and K2 are increasing, I see that the mean will be converging to 1, right? K2 by K2 minus 2, the mean will be converging more and more to 1. And if K1 and K2 are coming closer to infinite, even the F distribution is also coming closer and closer to a normal distribution. And a few more things. Even there is a relationship between the T and the F distribution. The square, see, if at all there is a variable that is following a T distribution, the square of the variable, if X is following a T distribution, the square of the variable which is following a T distribution generally follows an F distribution with parameters 1, k. Right? If X is following a T distribution with k degrees of freedom, and X squared will follow an F distribution with parameters 1 and k. That's a kind of relationship that is existing between the T and the F distribution. Another interesting aspect to be looked at. Then I'll be now looking at two other distributions, which is a triangular distribution and a beta distribution, which fall into a different class of distributions where there is a fixed minimum value and a fixed maximum value. Probably your uniform distribution is one example of that group. You have a fixed minimum and fixed maximum. Probably I say U0, 1. So it's any value between 0 and 1. But in the uniform distribution, everything looks very much straightforward. Or the probability of occurrence of any value is more or less constant. But there could be many variations on the top of that. But these two distributions, the triangular and beta, they are more and more applicable for those kind of data which vary in a fixed range. Probably I want to model probability of default. I know that it lies only between 0 and 1, right? So I could have used the uniform distribution, but the uniform distribution, the probability is constant, so I should not use that. So this is where I am looking at a couple of other distributions. So in case of a triangular distribution, the PDF is more like a triangle. The probability density function. In case of uniform, we have seen this is the flat, constant. Whereas in case of triangular distribution, the probability density function is a triangle. So the range is more or less finite, slightly more complex compared to a uniform distribution, but there is a lot of flexibility. And a few more important points. The triangular distribution is a unimodal. There is one single mode. It can be made symmetric. The good thing is it can be made either symmetric or positively skewed or negatively skewed. So I can create it by changing the parameters. I can make it in any manner. So let's say that I'm talking about a triangular distribution with the range of A to B. And let's say the mode of that particular distribution is C. Then the typical PDF for it is actually divided into two parts. One is between A and C, and the other one is between C and B. Between A and C, the probability density function looks like 2 into x minus A divided by B minus A into C minus A. Whereas between C and B, it comes out as 2 times B minus X divided by B minus A multiplied by B minus C. So this is what will be the probability density function between A and C, where C is the mode. And this is the probability density function between B and C, where C is the mode. So if you substitute x equal to A, probably this is 0. So the PDF is 0 at A. PDF is 0 at x equal to B. And what about C? At C, it is nothing but twice C minus A divided by B minus A into C minus A. So 2 by B minus A, whether I substitute it here or here, my mode is 2 by B minus A. Right? At C, the value of my PDF is 2 by B minus A, 2 by the difference between the minimum and the maximum value. And a few more attributes associated with it. If I am looking at the mean of this triangular distribution, which is nothing but A plus B plus C by 3, and I am looking at the variance, it is A squared plus B squared plus C squared minus AB minus AC minus BC divided by 18. So that comes out as the variance of this triangular distribution. So some of the important formulas for us to remember and use. Then moving on to the next distribution, which is also a fixed minimum, fixed maximum distribution, beta distribution, where the range is fixed. Slightly complicated compared to the triangular and uniform distribution, but makes it more and more flexible. Especially for default rates and recovery rates, again which lie between 0 and 1, we try to use the beta distribution. And this is heavily used in Bayesian analysis as well. So there are different applications of the beta distribution in the world of finance and risk management. The probability density function comes out like this. 1 by beta times beta of AB, x to the power of a minus 1 times 1 minus x to the power b minus 1. So the beta is a function, the formula associated with the beta function, and it comes out as x to the power of a minus 1 into 1 minus x to the power of b minus 1, where x lies between 0 and 1. So beta is a beta function. The typical way of expressing the beta function is nothing but it's an integration where I'm looking at between 0 and 1. If I'm talking about beta a comma b, it is nothing but it's an integration of x to the power of a minus 1 into 1 minus x to the power of b minus 1 dx. Integration between 0 and 1, x to the power of a minus 1, 1 minus x to the power b minus 1 dx is nothing but your beta function. And if you are setting a equal to 1 and b equal to 1, so it is simply x to the power of 0 and 1 minus x to the power 0. And then that is nothing but, so you're integrating it 0 to 1 dx, where value is constant. So the uniform distribution is coming out when a is 1 and b is 1, associated with the beta distribution. And coming to the other computation, the mean of a beta distribution is a by a plus b, and the variance of a beta distribution comes out as ab by a plus b squared times a plus b plus 1. So again, for the beta distribution also, we have different kinds of calculations that we can do. Then we are moving on to another important aspect called as the mixture distributions. Till now, for understanding the mixture distribution, something that is important for now, look at the stock. I know that the log returns of that stock, they follow a normal distribution. But this log returns, I don't want to take them normal for all the time. Probably I want to break it. 90% of the time, they follow a normal distribution with low sigma, and 10% of the times they follow a high volatility, but they still follow a normal distribution. So probably at some particular points in time, their volatility could be much higher, some news coming up, some explicit point in time where I want a different behavior to come out altogether. And this is where we are talking of a mixture distribution. So f of x, I am talking about some different f of x, let's say a low volatility f of x multiplied by the weightage, or 90% of the time this could be the case, and another f of x where I am talking about high volatility multiplied by the weightage of high volatility. This kind of a distribution where I am saying 90% of the returns are coming from low volatility normal distribution and 10% of the returns are coming from high volatility normal distribution. So if I have to generate something of this kind of a sort, this is where we have to rely on Monte Carlo simulation, and the final one, whatever is going to come out, may not be a proper normal distribution here. It may be its own distribution. It may be it may not be a proper normal distribution, but it may be its own distribution in its own right. Right? So it's not the same as adding two random variables. They are not independent and they are not too different. For the same one, we are talking about generating with a weightage, some particular value being generated, from some distribution and with some other weightage, some other value getting generated. These kind of distributions are typically called as the mixture distributions, where I can really identify what could be the weight, right? I'm looking at all the possible distributions along with their probability of occurrence of each of those distributions. And the combined, I may not have any kind of a name for that combined distribution, but they are very extremely flexible. So there is a parametric part. So the names of these distributions are parametric, but the weights that I am giving to them may be completely based on historical observation. So I may still make them non-parametric. So there is a trade-off between a parametric and the non-parametric kind of distributions. So how many distributions I may want to use? This could be one distribution, this could be other. I can increase many number of distributions and I can mix them as well. My model becomes more and more complicated, but I may be very closer to replicating the reality as well. So when we are adding two normal distributions together like this, I can generate any kind of a distribution, right? Probably if this is having, if these are having two different means, I can generate a bimodal kind of a distribution. Or I can combine two normal distributions with the same mean but different variances, which could generate something with a very excess kurtosis. Or if I'm changing the mean of one distribution, I can make it positive skew or a negative skew. Or if I'm changing two different means, if I'm making the means completely different, I can create a bimodal kind of a distribution. So the mixture distributions from that perspective become more and more important, and they play a very important role in the world of risk management. So the securities whose returns are either skewed or they are having excess kurtosis, I should really look at them as the ones which are more riskier compared to the normal distribution, because the extreme events are going to occur more and more frequently. In that case, it's better that I model them using the mixture distributions rather than a simple normal distribution itself. So that's how understanding of the different kinds of distribution can really help us targeting the business problems more and more effectively and help us to typically play a big role in the world of risk management. So that is what I wanted to look at in this session, where we have covered different kinds of distributions, from discrete distributions to continuous distribution to the distributions whose values are limited in a fixed range, and the distributions which are mixture distributions, understanding the concept of the central limit theorem. So this chapter becomes more and more important from the real world application perspective. Thanks a lot for listening to this session. Thank you very much.